Kiran, good afternoon.
Good afternoon, sir.
Anantnarayan, good afternoon.
Good afternoon, sir.
Uh, Akash, good afternoon.
Good afternoon, sir.
Akshay, good afternoon.
Good afternoon, sir.
Sai Charan, good afternoon.
Good afternoon, sir.
Nayan, good afternoon.
Good afternoon, sir.
Deepanshu, good afternoon.
Good afternoon, sir.
Naveen, good afternoon.
Afternoon, sir.
Arvind, good afternoon.
Good afternoon, sir.
Can you see my screen?
Yes, sir.
Anish, good afternoon.
Good afternoon, sir.
Some problem in recording. Can any of you do screen recording?
So Sanjeevi can record the screen.
Bharat?
Yes.
Okay. So because now it's not working, it is temporarily unavailable or something. Yeah. Okay, then you can start recording. Okay, hello everyone. Good afternoon, all of you. So we start with today's quote by Buddha. So he says, as a bee gathering nectar does not harm or disturb the color and fragrance of the flower, so do the wise move through the world. So we also should be like that. In our way of living, you may be greedy, you may be having your own motives, you may be wanting something and all. Whatever you do, okay, may everybody live for their selfish needs only. But in doing that, we should not harm or affect the surroundings or other people. So that is very important. We should not disturb, like a bee does not disturb the color and fragrance of the flower. So we should not disturb the world around us, other people around us because of our presence. And today is the birthday of Henry Martin Lalande. Okay, so he has a lot of contribution in automobile industry. He is an American inventor and industrialist who founded Cadillac Motors. Cadillac cars, I think you know about it. So in 22nd August 1902, to build the Cadillac, the first automobile with high precision, fully interchangeable parts. Earlier in his life, he had learned precision tool making, making rifles during the Civil War, invented the first mechanical barber's clippers, and made engines for Oldsmobiles. When Lalande designed an improved engine, but Olds did not want to adopt it, Lalande started his own industry, Cadillac, to build his own brand of automobile. He eventually sold the company to Will Durant's General Motors Company during World War I, and he formed a new company to manufacture aircraft engines, which after the war he produced a new automobile, the Lincoln. And that company was brought by Henry Ford. So you can see he has a lot of contribution in the automobile industry. So today we discuss about a problem in centrifugal compressors. And before going to that, just we will revise what we had done in the last class. So we had discussed about the concept of slip. Okay, what is this slip? So whenever there is some movement takes place, there will be inertia of the fluid inside that. And because of that, there will be an opposite motion induced into that. So because when the centrifugal compressor rotates, it will induce an opposite rotation on each particle on that. Its spin, opposite spin. And because of that, there will be a relative eddy is induced between the compressor blades, due to which there will be a negative whirl component introduced at the periphery of the impeller, and due to which there will be reduction in CW2 at the impeller tip. So that is the concept of slip. So how much it is reduced? So this is defined as slip factor. Slip factor is the ratio of the CW2 with slip and 2 without slip. And so the quantification is done by Strodola's model. So that is sigma, the sigma given to it. And it is approximately usually 0.9. You cannot avoid it, right? It is inherent in the character of the fluid. Nature creates that. Then work input factor. It is due to the windage losses or the disk friction losses, due to which for a given pressure ratio, I have to supply some additional work. So that is given by psi. Some 4% of additional work I have to give. So usually the approximate value of work input factor is 1.04. But again, if slip factor and input factor are given in our as far as problem is concerned, if they are given, you can use it. Otherwise, you need not use it. And then we have derived the expression for pressure ratio. So first of all, work is equal to, if it is UW2 CW, U2 CW2, and slip factor, if you introduce, it will become sigma U2 square. And if you introduce work input factor, it will be psi sigma U2 square. So that is the work, which is also equal to Cp into T03 minus T01. Okay, so that is the work. And pressure ratio we have already derived. The pressure ratio is equal to 1 plus eta C W by Cpt01 to the power of gamma A by gamma A minus 1. So substituting that, we can get the expression for pressure ratio. So then we have seen what are the factors that affect the pressure ratio. So there, because psi, sigma, eta C, Cp, T01, gamma, everything, we don't have any hold on that. Okay, Cp and gamma can be varied if you change the working fluid, but normally for aircrafts and all, air compressor only we will use, and air is the working fluid. So only U2 is the one which influences the pressure ratio. So the more you increase the speed, the more increase in the pressure ratio. So the U2, the value of U2 decides. So U2 is restricted by the centrifugal stresses. So I cannot have too much. And so if you have normal materials that we use, we can go up to 350 meter per second. And if you have titanium blades which can withstand those high centrifugal stresses, we can go up to 450 meter per second. So in the last class, you people have calculated using 350 meter per second and 450 meter per second. So you can see that we can go up to some 4.3 or 4.4 like that. So if you have good material. And then we talked about the inlet guide vents. So if though the inlet velocity may be subsonic, the absolute velocity CA, right, if it is subsonic, but the relative velocity may become supersonic and it may create shock. So usually the blade velocity at the tip of the eye is the more. And so the V1, the relative velocity at the impeller eye tip, right? So will be the maximum. So you have to check whether that is going beyond the supersonic or sonic velocity or less. So if it is going beyond sonic velocity or say approaching supersonic, then it is always it may create damage, it may create shock and damage to the impeller. So I have to have a process of reducing the velocity, and that is done by inlet guide vanes. So what inlet guide vanes is doing is, so when the flow comes axially, it just tilts it by introducing some will component, so CW1, and that is called as pre-whirl, and the angle by which it is deflected is the angle of pre-whirl, due to which the V1 will get reduced. So I can avoid shock by introducing inlet guide vanes and introducing pre-whirl at the inlet of the eye. But it will create a reduction in the pressure ratio because the work is equal to U2 CW2 minus U1 CW1. So CW1 is not 0 now. It will have some value. So U2 CW2 gets reduced by U1 CW1. Okay, so that reduces the work. So work reduces the pressure ratio because in the expression of pressure ratio, 1 plus eta CW by CPT not 1 will be there. So the W gets reduced. Okay, then we have seen dimensional analysis. So we have seen what are the parameters that affect the performance. So we have taken T01 and RT01 and P03, RT03 at the exit and inlet, and then the diameter of the impeller, and we have taken the RPM, the speed of the impeller, the mass flow of the compressor. These are the flow parameters we have considered. So because there are 7 parameters and 3 fundamental parameters MLT are there, so we have found that there will be 4 non-dimensional parameters, out of which we got the analysis and we got 4, and one is P03 by P01, which is the pressure ratio, and then RT03 by RT01, which is T03 by T01, which we have replaced it by efficiency, and then a non-dimensional speed we got. There ND by root RT01 you will get, and which is like rotational Mach number, right? We can assume it like Mach number based on rotational velocity, so rotational Mach number. But removing the diameter and R, assuming it to be constant for a particular impeller at a with a particular working fluid, that is air, so we can write it as N by root T01. That is the third one. And the fourth one is non-dimensional mass flow. So non-dimensional mass flow, again, it is like a Mach number. We have seen that. And it is called as flow Mach number. Again, removing D and R there, we are going to get M dot root M dot P01 by root R, M dot P01 by root T01. Okay. So that is the way we get. And then we have seen how the characteristics will be. So if you remember, some more points I wanted to discuss. So characteristics, if you see the head flow characteristic, that is psi and phi. So we got this something like this. This is for backward curve. and this is for radial, and this is for forward curve. Okay, and here this is having negative slope, and this is having horizontal, and this is forward is positive slope. So we think that, okay, because this may be good because with flow the pressure ratio increases, but it is against nature, so it always gives an unstable performance. It gives unstable performance. So normally forward curved vanes normally is not used. Okay, and we use either radial vanes or the backward curved vanes. Even the radial vanes are backward curved vanes also. If radial vein, the backward curved vanes are there, the characteristic will come like this. And for radial vein, the characteristic come like this. Okay, so these are losses. Okay, these are losses. So this is the straight lines are ideal characteristics. These are real characteristics. It will come like this. Even within this also, and we normally prefer backward curved vanes for industrial applications. And so if the so when the rotation is in this way, backward curved vanes are like this, opposite way. So here, because it is rotating this way, because of the centrifugal forces, actually the any particles or mud-like things, actually this is actually what I call is self-cleaning. So the self-cleaning is more in backward curved application, backward curved vanes. So they will be pushed out smoothly out because of the bend is in the opposite direction. So the self-cleaning characteristic is there with backward curved vanes. So this is one of the advantages. And one more thing is if the speeds are very high, and there will be centrifugal stresses acting on this, and they will try to straighten the blades straight. Okay, large RPM will try to straighten the blades, and it creates large stresses. But if I have radial vanes, right, there will not be any problem because they are already straight. So the backward curved vanes will try to become straight, but they are rigid. Because of that, there will be stresses on that. But radial vanes are preferred for high speeds and therefore used in aircrafts. And also aircrafts work in clean atmosphere, right? So I don't need that self-cleaning characteristic much for the compressors. The centrifugal compressors are used in the higher altitudes where the atmosphere is clean. Okay, so this is the main difference I wanted to make you understand. And other thing I already discussed that within this particular curve, and I can use only to the right side of the peak. Okay, so this is called as surge point. And this is again restricted at the end by choke. Okay, so this is limited on the left side by surging and the right side by choking. So only a part of it can be regularly, practically applied. So because of that, when I do it at so like when you do it, so we'll have something like this and the curves like this, and this is very okay, and this is called as surge line. Okay, this is the centrifugal compressor. performance characteristics. Okay, it will come like this, and if you put efficiency there, okay, drawing both of them. So if I draw efficiency, so I'm going to get curves like this. Okay, so okay, so whenever you purchase a compressor, these characteristics will be supplied to you. Okay, so we have discussed about these dimensionless parameters, performance characteristics, and surging. Okay, so this is about the theory. And so coming to the problem, so we will consider a problem. Okay, usually you will be given, if at all it is there, so psi will be given power input factor. So 1.04, some sigma is equal to 1.9, and the speed will be given to you. It is given to be 290 RPS. And you have to be careful here whether it is given RPM or RPS. Okay, so if it is RPM, then U equal to pi dn by 60. Otherwise, just pi dn you have to. And mass flow will be given to you 9 kgs per second. And ambient conditions. And diameters will be given, impeller tip diameter and impeller eye tip diameter and eye hub diameter, I think maybe 0.5 meters, 0.3 meters, 0.15 meters, like this. And ambient conditions may be 1.1 bar and 295 Kelvin. And efficiency will be given to you. I think it is given as 0.78. Like this. Okay, this is the data given. And you are asked to calculate to determine the pressure ratio of the compressor and the power required to drive it, assuming that the velocity of the air at the inlet is axial. Okay, so what is the meaning of that? Assuming that the velocity of the air at the inlet is axial means there is no ICV. Okay, so at the inlet of the eye, if it is axial, I don't have ICV, which changes the direction, which introduces free will and all. So CW1 will be equal to 0. So that's what it indicates. Okay, so first we will see that we are asked to calculate pressure ratio and power developed. Okay, so we have the formulae like W is equal to psi sigma U2 square. And pressure ratio is equal to 1 plus eta C W by CPT naught 1 to the power of gamma A by gamma A. Okay, these are the formulae you have. And so psi is given, sigma is given, and U2 can be given because the impeller tip diameter is given. So U2 is equal to pi d2 n by 60 will not be there because it is RPS. Okay, so pi d2 n, this will be in meter per second. And once it is given, so W can be obtained using this. And what is power? Mass flow into work, isn't it? M dot W. Okay, so this will be power. And so power can be calculated and pressure ratio can be calculated. Will anyway, can you tell me the values? Can you tell me the blade speed that you get? .5
5
Okay, 5 to whatever it is. And so I can calculate W psi sigma U2 square.
One 194.227.
194, huh? How much?
194.227 to 10 to the power 3.
0.23. So I can find out
Into
the
10 to the
power.
power 3, sir.
What is that?
10 to the power 3.
Into 10 cube.
10 power 3. Okay, that is I can write this kilojoule per
Yes,
kilo.
sir. Kilojoule per kilo.
Yes.
So if you multiply by 9, you will get in kilowatts. So can you find the power?
1748.05 kilowatt.
Okay. Okay, this is the power. And now you can calculate the pressure ratio. Gamma A is equal to 1.4. And gamma A by gamma A minus 1 usually 3.5.
5.944.
5.944.
Yes.
Is it right? Anybody else can try? Is that okay? We will see. Pressure ratio, it is 4.23 only. Just to check it.
Yes. Yes, sir. 4.24, I saw. 4.24.
4.23, right? R is equal to 4.23. Okay. So these are the things calculated. And next what is asked is to calculate the inlet angle of the impeller vane at the root and tip radii of the eye, assuming that the axial inlet velocity is constant across the eye annulus. Okay, means if I take this as the eye, so this is our hub and this is tip, and from throughout it is assumed to be CA to be constant. Okay, so as I told, you will change from here to here because this is the axis. So this is R I hub. This is R I tip. Okay. So you will be changing. So you will be changing. CA is constant, means we will change. Okay. So you also will change. So here, if I draw the velocity triangle, so this is CA. Like this is hub, this is mean, and this is tip, this is U, right? And this is CA. And these are velocities, relative velocities. V1 at tip, V1 at mean, and V1 at hub. And this is the angle beta 1, beta 1 H, beta 1 M, beta 1 tip. You are asked to calculate the beta. So this is the angle at which it is entering the eye. So this is asked. So you can calculate U, no problem. You know the hub hub diameter and tip diameter. So I can find out the mean diameter. I can find out all the diameters. So once I know diameters, I can find out what is U at each radius because RPM is known. So in that way, I have to find out what is U at hub, mean, and tip. But I have to know what is CA. So how to get CA? CA is the flow component. So CA m dot is equal to rho A, rho 1, A1, CA1. Okay, so A1 is known because this annulus area A1 is equal to pi by 4 d I tip square minus d I hub square. Okay, A1 is known and mass flow is known. But rho 1 and CA1 is not known, rho 1 also is not known. But instead of rho 1, we are given the pressure and temperature at the entry. So P naught 1 is equal to 1.1 bar and T naught 1 is equal to 295 Kelvin. These are the values given. But these are stagnation conditions. The ambient conditions, whatever are given, they are stagnation conditions. Why? Because suppose compressor is not started. Okay. So outside air is, ambient air is stagnant. So they are stagnation conditions. So it is sucked. When it starts, it sucks. It sucks means there will be some velocity and the pressure and temperature, they will have static conditions. Is it clear? So I have to find out the velocity at which it enters. And for that, I have to know that density. But density, static density I need. So for that, I need static conditions. So how to get the static conditions? So here I have to do an iterative calculation because T1 is equal to T01 minus CA square by 2CP. CA or C1 because C1 equal to CA. CW1 equal to 0. Okay, so T01 is CA square minus 2CP. And how to get P01? So P1 by P01 is equal to T1 by T01 to the power of gamma A by gamma A minus 1. Then rho 1 is equal to P1 by RT. Okay, so if I calculate like this, then this rho 1 can be used to get CA1. CA1 is equal to m dot by rho 1 A1. But how to get this? Either CA should be there or rho 1 should be there. Okay, so I have to approximate some value. Usually, there are various methods of approximating or iterating. First, initial value, how to take. So one way is CA normally will be around 150 meter per second. You can take some initial value as CA 150 meter per second. Or the other way is P01, T01 are given. So rho 01 can be calculated. P01 by RT01. And this can be taken approximately as rho 1. If this is taken as rho 1, so then first calculate CA1 and then calculate T1, then calculate P1, then calculate rho 1 and check whether both are same or not. Or you take 150 meter per second, right? So using that you calculate T1, then calculate P1, then calculate rho 1, then calculate CA1 and check whether the values are okay or not. Or some 2 iterations or 3 iterations you have to do. Am I clear about it or not?
Yes, sir.
Okay, so we will do that right now. So what I will do is, actually in the textbook, he has taken this method of taking rho 1 approximately equal to rho 01 is equal to P01 by RT01. Okay, this is the way he has started and doing it. So we will do the other way. CA1, you can take it as 150 meter per second. Okay. And CA1 actually should not be too high or too low. This is also some reason. So as CA increase, actually mass flow increase because rho 1 A1 CA1. But frictional losses increase as the velocity increase. So I have to compromise some value, and usually this is the best value. And not only that, as CA increase, V increase, V1 increase, and V1T may cross sonic and may result in a shock. Okay, so these are the things restrict the value around 150 meter per second. So if I take CA1 as 150 meter per second, so I have to calculate T1 is equal to T01 minus CA square by 2CP. T01 is 295 minus 150 square by 2 into 1005. So can you tell me how much it comes to?
$283.80.
283.8. Huh? Then P1, because P1 by P01 is equal to T1 by T01 to the power of gamma A by gamma A minus 1. So I can get P1 is equal to P01 is 1.1 into T1 is 283.8 by 295 to the power of 3.5.
0.96.
0.96.
96.
96. So now rho 1 is equal to P1 by RT01. So that is P1 is 1.1. Actually 1.1, this is bar. So if I take it as 10 square kilopascals, and so 0.287 into T01 is 290. So here units, you have to be careful about the units, right? How much?
1.17.
1.17?
17.
Okay. Okay, rho 1 is there. So CA1 I can calculate now. So before CA1, I have to calculate A1. A1 is equal to pi in by 4 DET square minus DEH square.
So density is coming out to be 1.3 approximate, 1.29.
1.29, huh?
Yes, sir.
Sir, here we are taking T01 instead of T1.
Yeah, T1 I have to take, right. Sorry. P1 by RT1, sorry. T1 is 283.8. Okay. So 1.35.
35.
So here pi by 4 DET square, that is how much we have taken 0.3 minus 0.15. How much this comes to?
0.053.
0.053 meters square. So I can get CA1 now. CA1 is equal to m dot by rho 1 A1. So that is 9 by 1.35 into 1.053.
125.7.
1
25.7.
0.7.
Okay. So now we got 125, and using this 125, now I have to repeat this calculation. Okay, so I will take around 126 I will take. Okay. So are you sure about this?
So 125.786. So it's
Okay. So that is 126. So now if I take it as 126 meter per second as the first next iteration, So what are the values I'm going to get here? I have to repeat this cycle.
287.1.
287.1. And then this
1, sir.
1 bar. And this
1.214.
1.214. So then what happens to this?
Uh, 139.87.
139.8. Okay, so one more equation is needed. Okay, so it is 140. This is 140 I am getting. So I take 140 as the next approximation. Now you try to repeat that.
285.24.
285.24. And pressure
0.977.
0.977 bar. And this is
1.194.
and finally this CA
142.1.
142.
142.169.
169.
15, sir. 1516.
1.
So this is the way we got. So we will see how the textbook he has done. So he has taken rho 1 as approximately P01 by RT01. So he has got some value 1.3. So CA1 m dot by rho 1 A1, he got 131 meter per second. So C1 square by 2 Cp and T1 equal to T01 minus C1 square by 2 Cp and P1 equal to P01 by this one. So P1 he got this and rho 1 is P1 by RT1 and CA1 he got 140 meter per second. So first approximation he got like this. Actually, we also got 140, and this 140 he has taken 145 later because he expected that maybe some more. It is like over relaxation, right? So he has taken 145. So using 145, he calculated C1 square by 2 Cp T1, P1, rho 1, and CA1. He got 143. Okay, so it is equal, both are very near. So he has fixed it to 143. So we got 142.2. It doesn't matter. So that is the way we have to decide about that. Okay, now suppose CA equal to 143 or 142. Okay, according to textbook, we will say 143 meter per second. Okay, now this velocity triangle. So U1 at hub, mean, and tip. Okay, and so if this is beta, this is U, and this is CA. So if I want beta, and beta 1 is equal to, how can I take it? Tan beta 1 if I take, tan beta 1 is CA by U. Okay, so we'll calculate at hub. CA is constant, hub, mean, and tip. So at hub, U I hub is equal to pi DE hub into M. Can you tell me what is the value?
Sir, is N is 290, sir.
N is 290 meter RPS.
D hub is 0.15, right, sir?
Yeah, D hub is 0.15 meters.
Then it's 136.66.
Yeah, 67 I will take. Okay, so beta 1h is equal to tan inverse 143 by 136.67. Can you tell me what the value?
.29.
Okay, I will take 3 degrees. And at tip, UE tip. So it will be double of that. Okay, so I think 273.34 meter per second. And so beta 1 tip is equal to tan inverse 143 by 273.34.
27.6.
27.6.
27 points. So if you are asked to find out at mean also you can find out UE mean is equal to actually average of these two you will get, or you can get DEM. DE mean is equal to DET plus DEH by 2, or 0.3 plus 0.15 by 2, 0.45 by 2, 0.225 meters. Okay, like that you will get. So UE mean will be
290.98. Sir. 204, sir. 204. Sir.
204,
Yes. 204. 205, sir.
205 meter per second. So beta 1m
34.89.
So it will come in between these two, right? Hub and tip. Okay, this is the way we can find out the inlet vane angle at the eye. And sometimes you may be asked to check
So
what.
beta 1 is coming out to 34.89.
Okay, 34.9. That's okay. And so here, this is V1T. And if I want V1T, how do you get? V1T is equal to root of
Diameter at tip diameter.
A square plus UI tip square. Can you tell me how much is this?
G 0826.
How much?
308.5.
308.5 meter per second. So if I want Mach number with respect to V1T is equal to V1T by the sonic velocity is gamma R T1, and R is 287 and T1 is the value is there, isn't it? How much it is? T1 is 287, 285.24. Can you find how much it is?
0.911.
0.911. Okay, so fortunately, it is not crossing sonic velocity. Okay, this is the maximum velocity we get because it is at the tip. Okay, so this is the way sometimes we have to check whether it is going beyond. So if it is going beyond, when I am designing, I have to keep IGV there. Okay, so this is the calculation at the I. Okay, so something we have to done at the exit. So we'll see what is that he has done here. So peripheral speed. So alpha at root 46.33, 27.65. Like this he got. I think we also got the same values. 46, 27. Yeah, 46 and 27. And so what else is asked is, yeah, to calculate the inlet angle is okay. To estimate the axial depth of the impeller channel at the periphery of the impeller. At the periphery of the impeller, So this width it is asked. That is B2 is equal to how much? This is B2. That is R2. Okay. Okay, so this B2 is asked, and we know that mass flow is equal to rho to A to CR. And A2 is pi D2 B2. And to know that, I have to know rho 2 and CR2. Then I can find out because mass flow is known. So here we make some assumptions. And so the data, one more, okay. We make two assumptions. One is CR2 approximately equal to CA1. This is flow component at the inlet and exit. Okay, this is the flow component at exit and flow component at the inlet. This is assumed to be almost same. Okay, so this is known. So how to get rho 2? So for rho 2 is equal to P2 by RT. Okay, and so here T2, okay, we know work is equal to Cp into T03 minus T01. Work is calculated, so this gives me T03, and we know that T02 is equal to T03 because 2 to 3 is a diffuser, so T0 is equal to constant. So T02 can be calculated. And another thing is CW2 is known. CW2 is equal to sigma U2. Because sigma is known, I can find out CW2. So CW2 and CR2 are known. So C2 is equal to root of CR2 square plus CW2 square. Okay, so once I know C2 and T02 is known, so T2 is equal to T02 minus C2 square by 2Cp. So T2 can be obtained. And how to get P2? P03 is known because R is calculated. R is equal to P03 by P01, which gives me P03. But how to get P02? For this, the second assumption that we make is the losses are equally divided between impeller and diffuser. Okay, this is assumed. Okay, what is efficiency? Efficiency is equal to 78%. So total losses is 100 minus 78, that is 22%. So by this assumption, there is 11% loss in impeller and diffuser. So therefore, efficiency of impeller, if 11% is the loss, what is the efficiency? That is 89%. So then I can use that pressure ratio formula. I can write P02 by P01 across impeller, okay, is equal to 1 plus eta impeller W by CPT01 to the power of gamma A by gamma A minus. So instead of 78, I put 89 there so that I will get what is the P02. Okay, so this gives me P02 and I need P2. So again, T2 by P02 is equal to T2 by T02 to the power of gamma A by gamma A minus 1. So this gives me P2. So rho 2 is equal to P2 by R2. And A2 is equal to m dot by rho 2 CR. And then because this is equal to pi d2 b2, b2 is equal to A2 by pi d2. Okay, so this is the method I have to follow. So we will do that. Okay, first CR2 is equal to, I will take same 143 meter per second. And CW2 is equal to sigma U2, and sigma is 0.9, and UT is how much? First, initially we calculated U2. How much it is? 4.5 meters. So how much it comes to?
Four not 9.95.
409.95.
109.95. So I can calculate C2, CR2 square plus CW2 square.
434.17.
434.1. Okay. Now T02, so W is equal to Cp into T03 minus T01. So T03 is equal to T01 plus W by Cp. T01 is 295 plus W is, just you check the values. So W is 194.23. How much this comes to?
488.26.
488.26. Okay, this is equal to T02. So I can calculate T2. T2 is equal to T02 minus C2 square by 2Cp. So 488.26 minus 434.1 square by 2 into 1005. So you have to check where I have to put 1005, where I have to put 1.005. So whenever velocity square is there, it will be in joules, not kilojoules. So that's why I have to put in 1005, not 1.005. So you have to be careful about that units.
394.507.
394.50 Kelvin.
So
Okay, so P02 I have to get now. So P02 by P01 is equal to 1 plus eta CW by Cp T01 to the power of gamma A by gamma A. That is equal to 1 plus eta impeller, right? So 0.89 into W is
194.23.
194.23 by 1.005 into 295 to the power of 3.5.
4.99.
1.102.
1.10. No. It will be something like this one.
4.99,
Yeah,
sir.
4.9.
Yes, sir. 4.9.
Yeah. So here you should not get confused. Actually, will P02 be more or P03? Which will be more?
P03.
So we will think P03, but P3 will be more, but not P03, because P02 to P03 it is a diffuser, not to 2 to 3 it is a diffuser. Okay, stagnation temperature remain constant, stagnation pressure decreases because of the losses. Nozzle and diffuser, stagnation pressure decreases. Am I right?
Yes, sir.
So P02 will be more than P03. After decreasing, we will get actual P03. So P02 will be more. That we have to check, right? Careful. So P02 is equal to 1.1 into 4.99 because P01 is 1.1.
5.49.
5.49. Okay, now I have to get P1. P1 is equal to P01 into T1 by T01 to the power of gamma A by gamma A minus. So P01 5.49. Sorry, all twos are there. And T2 by T02. T2 is 394.5 by T02 is 488.26.
2.6.
2.6. So rho 2 is equal to P2 by T2. And P2 is 2.6 into 100 by 0.287 into T2 is 394.
2.298.
So now A2 is equal to m dot by rho 2 C out. That is 9 by 2.298 into 143.
0.0273.
So now B2 is equal to A2 by pi D2. D2 is 0.5 meters.
0.01.
0.0173.
Meters means 1.73 centimeters, right? So this is the way we get. So we'll just check what is that. Yeah, right. So 1.76 centimeters. So this is the way we have to find out what is the impeller width at the exit of the impeller. Okay, now coming to the diffuser. So after impeller, we have what is called as vaneless space. And then we have got diffuser. Okay. So usually exercise problems, they will not go beyond to this, but example problem he has done into the diffuser also, right? So in the vaneless space, it is assumed that angular velocity or it is like, okay, instead of that, we calculate it is okay, so RCW is assumed to be constant. In the vaneless space, RCW remains constant. So here D2 impeller exit D2 is known, and vaneless space, if it is given, I can calculate what is the D at the diffuser inlet. Okay, if you add that. So because you know the both diameters, I can find out what is CW at that point. And there again, I have to do the iterative calculation for CR. Okay. So how it is done, you can just see. So normally about coming to the diffuser, because as I told, there will be pressure increasing across the diffuser. That's why there is a adverse pressure gradient. And whenever there is adverse pressure gradient, there is a possibility of separation and the eddies formation and the losses. That's why there is a particular limit for the angle of the diffuser. And if you remember, even I think in hydraulic turbines, draft tube will be there. There also, the draft tube is like a diverging process. Okay, so whenever there is a diverging process, there is a limit of divergence angle. So usually it is the total divergence will be 14 degrees, and if it is this side, okay, each side it will be 7 degrees. Like that it will be. So this will be 7 degrees. And this will be 7 degrees. Total cone angle usually will be 14 degrees. It is limited. Okay, so that is a problem with the diffuser. You have to be careful. So we have to calculate actually the inlet angle to the diffuser. So to find the correct inlet angle for the diffuser, the flow in the vaneless space must be considered. Okay, so no further energy is applied to the air as it leaves the impeller, so that neglecting the effect of friction, the angular momentum must be constant. Means RCW is assumed to be constant. So hence CW decreases from impeller tip to the diffuser vane, ideally in inverse proportion to the radius. So for a channel of constant depth, the area of flow in the radial direction directly proportional to the radius. So the radial velocity CR will therefore also decrease from impeller tip to diffuser vane, right? Because the radial distance is increasing, actually the area is increasing. So velocity, naturally whenever there is increase in the area, there will be diffusion takes place. So in the vaneless space, there will be diffusion. As I told already, sometimes there may be diffuser vanes or there may not be diffuser vanes. If there are no diffuser vanes, just the area increase from this radius to this radius. So much area increase, and because of that, automatically diffusion takes place. But that diffusion will be sudden diffusion after the impeller, and there will be more losses. So to have gradual diffusion, I will have diffuser vanes. Okay. So because both CR and CW decrease, then the resultant velocity C will decrease from impeller tip, and some diffusion evidently takes place in the vaneless space. The consequent increase in density means that CR will not decrease in inverse proportion to the radius, as does CW, and the way in which CR varies must be found from the continuity equation. From the mass flow, I have to calculate CR. So this is important. Again, as I have calculated CA from the mass flow at the inlet, here also I have to calculate from the mass flow. So an example at the end of the session to show that when CR and CW have been calculated at the radius of the leading edge of the diffuser vane, then the direction of the resultant velocity can be found by, and hence inlet angle of the vane. So once I know CR and CW, right? So I can calculate what is the angle at which it is coming out. Here there will not be velocity triangle. At the inlet of the diffuser, there is only absolute velocity, no relative velocity, because it is not moving. So if I know CR and CW, I can find out what is the angle. Okay, so this is something like, consider the design of the diffuser of the impeller compressor dealt with in the previous example. The same example we continue. The following additional data is assumed. Radial width of vaneless space 5 centimeters. Okay, so vaneless space is 5 centimeters. So what is the diameter at the inlet of the diffuser? Impeller exit is 0.5 meters. 0.5 meters means how many centimeters? 500 centimeters. So in both sides, the diameter means both sides there will be 5 centimeters. So 10 centimeters I have to add. So 510 centimeters or 0.51 meters will be the diameter at the diffuser inlet. And here approximate mean radius of the diffuser throat. So here throat means, so I will have so this is the diffuser space. I will have diffuser vanes like this. Okay, I will have diffuser vanes like this. Actually, okay, if there are more number, and the biggest circle that I can draw here, right? And if I take the center, this is what is called as throat. Okay, so if I take the diameter here, that is the diameter at the diffuser throat. Okay, so that is the way it is. The depth of the diffuser passes, anyhow, it is calculated 1.76 centimeters, and number of diffuser vanes it is given to be 12. Okay, and required are the inlet angle of the diffuser vane. I have to calculate the inlet angle of diffuser vane. I need CR and CW at the inlet. Okay, CW I can calculate because RCW is equal to constant. Okay, so 0.25 is the R at the impeller exit, and 0.3 is the radius at the is 0.3. 0.25 meters, 0.05 meters, sorry. So 0.05 meters is the vaneless space. So the radius is 0.3 meters. As I told, diameter is 0.5 meters. So radius is 0.25 meters for the impeller. And this vaneless space is 0.05. So 0.3 meters is the radius at the diffuser inlet. So RCW is equal to constant. CW2 is 410, which we have calculated. So at 0.25 meters, so at 0.3 meters, I have to calculate 410 into 0.25 for 0.3. So 342 meter per second. And now I have to calculate CR2. Okay, so CR2, I have to iterate again. So this iteration, you can take around 100 meter per second usually. Okay, CW2 is equal to R2 CW2. And here he has taken 2 at impeller exit and also at the diffuser inlet. Okay, so you have to understand that these two, you should not get confused. Okay, CW2 or RCW. Okay. RCW2 at impeller exit is equal to RCW at diffuser inlet. Okay, so R is 0.25 meters into CW is, what is that we got? CW2 is 40 or 410, okay? 410 is equal to 0.3 meters into CW at diffuser inlet. So CW is equal to 410 into 0.25 by 0.3. Okay, this is what we get. So CR I have to calculate. So this I can assume. Okay, so if you assume some 100 meter per second, so C2 is equal to root of, I will write like this, CR2 square plus CW2 square. And within the vaneless space, P0 and T0 is constant if we neglect friction losses. Okay, because T0 is constant, there is no heat addition and work done. And P0 also is constant if there is no friction loss. So P0 and T0 are assumed to be constant. So I know P0 to T0 already, and C2 is calculated from here. So again, the same things, T2 is equal to T02 minus C2 square by 2 Cp, and P2 is equal to P02 into T2 by T02 to the power of gamma A by gamma A minus 1, and rho 2 is equal to T2 by RT2, and CR2 is equal to m dot by rho 2 A2. And what is A2? A2 is equal to pi D2 B2, and D2 is here 0.3 meters I have to take, and B2 already calculated 0.0176 meters. Okay, this is the way I have to calculate CR2. And this I have to check because I have assumed 100 meters per second, whether I am getting near to that. Okay, shall we do that? Calculate CW2. 410 into 0.25 by 100. Can you tell me CW2?
So 341.67 is CW2.
Yeah, C2.
So C2 came 356.
356. So you have to calculate T2, and T02 is T02 is 488.26. So this I have to keep 1005. T2 is
52 is 252.2.
okay. P02 5.49. How much for? How much?
420.
425.20.
Okay. So P02 into T2 by T02 425.2 by T02 488.26 to the power of 3.5.
3.383.
So then 3.383 into 100 by T2.
2.7728.
How much?
2.7728.
772. Okay, then we calculate CR2 now. A2 is pi into 0.3 into 0.0176.
Point 1843. No, wait, sir. Sorry.
Okay.
0.0165.
Okay, so then CR2 is equal to m dot by rho 2 A2, that is 9 by 2.772 into 0.0165.
196.77.
196. I think we should not get so much. There is somewhere we are done wrong. We have to get around 100 only. because it will decrease, right? There is somewhere we have done wrong. Is there any value P0 to T0 to anything taken wrong? T0 to 488.26, 5.49. Okay, anyhow, you have to do like this, and I don't know what is the value he has got. He got 98. Okay, just okay. Oh, okay. I think okay. I think we have done the wrong for the area. Okay, so pi d to b to this 0.3 is R2. Okay, here this is 0.6. Just can you please repeat this calculation? So this is into 0.2. So I'm going to get some 0.033, I think.
Everything will change, right? From our CW2 to.
No, we didn't use A only used at the end, isn't it?
But it's a density in.
We have not used the diameter or radius before this, right? So here only we are using this A2. So instead of 0.3, I have to use 0.6. So this will be 0.033. So this into 2.
98.08.
98. So you can see the same thing, right? So 97.6 he has taken. You got this 98. Okay, same 98 I got. So that is the way we get. And CR2 by CW2, it is just like velocity. Okay, so this is CR and CW, right? And if this is alpha 2. So we calculate the angle like that. So tan inverse CR2 by CW2. So we get the angle. This is the inlet angle for the diffuser vane. Okay, this is the way we calculate. Okay, we'll stop here. It's already 4:30. Okay, there is actually, he has calculated only one more thing. The throat width of the diffuser passes, which are assumed to be of constant depth. Okay, that depth is 1.76 centimeters only, and he has asked for throat width. Okay, this we will discuss in the next class. Okay, you have to go through the problems that are given at the end of the chapter, and also whatever are given in Ganeshan, whatever are given in Yahya. So these problems, example problems, if you see from the Ganeshan and Yahya, you can understand how to solve the problems, because next assignment will be the exercise problems given in the Sarvanamuthu. Okay, so there are two additional things may come into that maybe tomorrow class we will discuss. That is, if you have pre-will, how to take care of that. That is IGV or something if it is there. Or this is a stationary compressor. If it is an aircraft compressor, so what is the way I have to deal at the inlet, because it is moving, right? Those two things we will discuss in the next class. Any questions? So we'll go for the story. Right?
Yes, sir.
It's a real story. I think all people are familiar about this name, Sylvester Stallone. Are you familiar with this name?
Yes, sir.
Which movies you remember?
Rambo.
Rambo. Okay, so there are series. Rambo series are there, and beautiful action movies are Rocky series are there, and Expendables series are there. And all this you can see him. And if you see his biography, you can quickly see Sylvester Stallone was born on June 6, 1946, in New York City. His father was a hairdresser, and his mother was a former dancer. His mother, Jackie, had such difficulty in childbirth that forceps had to be used to assist Sylvester's delivery. And his signature sneer and his unidentifiable accent, which is actually slurred speech, were the result of nerve damage caused by the incident. Because he is a forceps baby, and so some nerves are damaged in the head. So you can see the way he talks in the movie, right? His speech will not be clear, and he also looks not like other heroes and all don't look smart and all, but he has physique, very right. And Sly, along with the younger brother Frank, was raised in a hostile environment. His parents fought a lot and later got divorced. He was not shown much affection in his home, and because he doesn't look good, and his speech is not, and he is like a retarded person, he is treated like a mentally retarded person. And he recalled his mother telling him that he didn't have a body he could work with, and on a separate occasion his father even told him that he didn't have a brain. Okay, such is like he's like a mentally challenged child. And Stallone was emotionally deprived of parents because both of them didn't love him properly, as he did not do well in school. And school also he didn't do well because he's so slow. As a matter of fact, he was expelled from school thrice. To make matters worse, after his parents got a divorce, he was sent to several foster homes. Okay, many people took him to adopt him, but because he's of his type, so many people left him again. And again, he is sent to orphan home, and like that, he eventually found his way back to live with his mother, and finally is given to his mother and attend a special school for troubled children. Okay, not a regular school. His childhood was clearly trying for the young Sylvester, but coming from such a difficult point in his life, he wanted to inspire people who were going through the same pains as he was. This was when he decided that he was going to be an actor. So he wanted to be an actor, he wanted to inspire the people like him. He went to Miami State University to study drama, but his desire was so overwhelming that he decided to leave school and head straight to New York. And Stallone auditioned tirelessly for castings in the city. So he went to every selection committee and for audition, and he was rejected many times. He was determined that this is what he wanted to do. Even when agents denied him, telling him that the business had no place for someone with an injured face, and even when his own wife told him to get a real job, he never gave up. He had made up his mind that acting was the only thing he was meant to do. So that is the passion one should have. And this caused Stallone to live in a small apartment without air conditioning and with a wife whom he fought with unendingly. The situation, though, did not kill his hunger for his real dream. He would go to castings and liberally work tirelessly to any role he could manage to get. He played small roles in a number of films and even got a starring role in a pornographic production. This he accepted, believing that it might lead him to bigger role, and partly just makes two ends meet because he is so poor. This venture did not go any further. However, it was difficult to get such small roles for Stallone, let alone get a starring role in any film. His apartment and his wife were cold and served him no comfort. He took comfort in the warmth of the city library, where he discovered his love for writing. Stallone did have a flair for storytelling, he discovered. So he found his strength. He would stay at the library or stay at his home, making up stories and scribbling certain scenarios. He was especially keen on inspirational stories where one overcomes an unbelievable situation like his own. For a time, he made a living selling these stories, but they were no bestsellers. And times were so difficult that Stallone even had to sell his dog just to get by. He was at his lowest point, but as they say, the night is darkest before the dawn. The story of Rocky Balboa was formed in Stallone's mind when he watched a boxing match featuring the great Muhammad Ali, and the underdog opponent Chuck Wepner managed to knock Ali out. At that time, Muhammad Ali was the biggest, and he has written a book, I Am the Greatest. Right? He was undefeated for many years, but he was just defeated by an underdog, Chuck Wepner, and he managed to knock Ali out. And Stallone was astounded and formed the idea of creating an underdog character who would overcome his trouble and rise to the occasion. So he went home and wrote the manuscript for Rocky. In 3 days, he had a screenplay and he had the vision of playing the starring role himself. He went to actor castings, still hoping to land a role in major film, but also having the freshly written screenplay in his back pocket. So Stalin went to a casting being conducted by Robert Chartroff and Irvin Winkler. When he didn't get the role he was aiming for, he offered his manuscript. Fortunately, the team considered reviewing the script and was quite impressed by what Stallone had written. They offered Stallone a large amount of money to buy the material. But they weren't happy, though, with the idea of him playing the lead role. And Stallone insisted that he play Rocky and wouldn't sell his script even when the offer was increased to ridiculously large amounts. His script was so great that finally, after heaps of negotiations, everyone agreed to let Stallone play the starring role. But his difficulties, however, did not end there. The movie was given a $1 million budget, barely enough to have a quality product. Stallone enlisted his family and close friends to play small roles in the movie and in the production. His wife was the set photographer, while his brother was an extra character. And the movie also took its toll on Stallone's body as he was not used to take that kind of activity Rocky was doing. During shooting, he would feel his body almost giving up and falling to the ground. Still, he pushed and convinced himself that the outcome would be tremendous if he could hold on just a bit longer. It was in 1976 when Rocky was released to the public and Stallone cashed in on his hard labor. Although he ended up spending days in bed nursing his sore body, the low budget film sold and inspired millions around the world. It also opened an avenue for Sylvester Stallone's acting, writing, and directing career. And he went on to star in over 40 films and is still active today at 67. His writing skills are unmatched, and as he continues to come up with action packed screenplays, he is also directing and producing high quality material. Being stubborn often has a negative connotation, but Sylvester Stallone's life struggles and his means of getting out of the ruts somehow debunked this idea. He was merely being stubborn, insisting on what he wanted and taking nothing else. Yet he achieved his dream and immense success followed thereafter. He has since then been the icon in the entertainment industry. He epitomized the age old proverb try and try until you succeed. He has proven there is nothing impossible when hard work and determination take action. And as for his dream, he has surely inspired and continued to inspire the whole world. So he says, no one will hit you harder than life itself. It doesn't matter how hard you hit back. It's about how much you can take and keep fighting, how much you can suffer and keep moving forward. That's how you win. He says, every time I have failed, people had me out for the count, but I always come back. So that is the inspiring character of Sylvester Stallone. Okay, thank you. Thank you very much. See you tomorrow.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
So Bharat, have you recorded?
Sir, it was Shubhankar, sir. He has recorded.
Okay, okay. To the participants also, the other people, group also you send, and to me also you send the link. Okay. Okay, thank you.
Thank you, sir.
Thank you.